Hello. Today we're going to be looking at the water tank activity. Some of us have already done this in class, but it's always good to have a refresher just in case you need it so that you're able to do it on your own, be able to follow it, you'll be able to pause the video when you're getting a little bit stuck, and then being able to slow down a little bit at times. But we're doing this activity for two reasons. Number one, because it teaches us some really helpful skills regarding modeling with linear functions, being able to come up with linear rules for real world situations, and of course, also for our PSMT as we look at how we can use linear models to model different situations as well. In this case, we're looking at this water tank activity and we want to look at this first scenario. Now, if you don't have your worksheet open already, you should have a worksheet open that you can find on MyRedeemer, the maths class page, or your OneNote, or if you don't know where you can find it otherwise, you can ask your teacher and they'll be able to get the worksheet for you. So it's recommended you have that worksheet out, print it out, and then you have a pencil and you can or pen, and you can just you fill out the worksheet as we go along. And hopefully, as you're filling it out and listening along, you're able to understand what's going on. So here's the context of the first scenario. A water tank is initially filled to 50 liters. This word initially is very important. It implies at the very beginning it's filled to 50 liters. A garden hose can fill the tank at 60 liters in 4 minutes. So this garden hose is being plugged into the water tank and it's filling this water tank at 60 liters every 4 minutes. The question being asked is, at what rate is the tank being filled by the hose in liters per minute? And of course, when time is equal to 0 minutes, what capacity of the water tank is already filled? Well, rate is pretty straightforward because it's already given us a clue here. It says liters per minute. You can see here a garden hose can fill the tank 60 liters per 4 minutes. So it's already in the right units. All we have to do here is take the 60 liters and divide it by 4 minutes, and we get, well, every minute it fills up around 15 liters, so it's 15 liters per minute. So that's all you have to do. Take the capacity in this case and divide it by the amount of time it takes to fill up to that. And of course, I talked about the word initially being at the very beginning. So when time is 0 minutes, as in if 0 minutes have passed, then the capacity of the water tank is of course just 50 liters, because that's what it says at the very beginning. Then very straightforward, we can use that to fill out a table for ourselves that sort of help us to understand exactly what's going on here. So 15 liters per minute. So in the first minute, right, how much is it being filled? Of course, it's already filled up to 50 liters, so that's the initial. And then we just add 15 liters, 15 liters, 15 liters, 15 liters, 15 liters, and 15 liters, because that is the rate that it's being filled at. And of course, you can see that the 50 liters here is what we will eventually call the y-intercept. When we see a graph of this, it will make a lot more sense. Of course, then we can come up with the rule in gradient intercept form, because we know that in this case, C we can define for ourselves. C is capacity in liters and T is time in minutes. Make sure when you're on your PSMT, before you write your rule, you're also defining each variable. And you're defining what units you're going to use. In this case, before you write the linear rule, you write something just before it saying where something, well, C is the capacity in liters and T is the time in minutes. Here we have the gradient. The gradient, if you have not already noticed, is just the rate. And we know this because if you look at the table here, that's the pattern being followed. 15 liters, 15 liters, 15 liters, 15 liters. That's the pattern. It's going up by 15 every time. That is why that becomes the gradient, because that's how much it goes up by every time. Every minute goes by, 15 liters goes up. And of course, we have the y-intercept, which is 50. As in, when time is 0, how much capacity is in the tank? Well, it's just 50 liters. So if you don't already know how to use Desmos and figuring out how to do that, there's another video on my channel that you can find. It's called something to do with Desmos skills or Desmos viewport and titles or labels. So go and look for that video so that you're able to understand how to do the graphing itself. But otherwise, I'm not going to do very much in that aspect. Here, I'm just going to show you exactly what happens. If you type this into Desmos and you get the viewport correct, which the other video teaches you how to do, you'll get a line that looks like this. And this line is the model that tells us the capacity at every single point in time of minutes. So that's helpful for us because, well, once we've done all the axis labels and putting everything in, which we teach you how to do this in the other video, you can see here that this allows us to see certain values because the graph tells us. So it says, according to the graph, how much water is in the tank at 10 minutes. Go to 10 minutes, which is between 0 and 20, so it's here, and see that it goes up to around, at this point in the line, so 200 liters is being filled at 10 minutes. Just like with 20 minutes, we go all the way up here, and we can see that it's around 250. Oh, sorry, this is 225, 250, 275. Oh, sorry, actually, that's 350. Oh, sorry, I didn't see that correctly. That's 200, 400, so it's 350. And finally, 40 minutes, if you go up to here, we can see that it goes to 600 and then 650 liters. Okay, so the graph visually tells you at certain values very clearly how much capacity is in the water tank at a specific point in time. What else you should know is that the rule itself can be used to figure out capacity at a specific time. And what we can do here is that we can see clearly capacity is equal to 15 times the amount of time taken plus 15 minutes. Plus 50 liters. So to find the capacity, all we have to do is take the 28 minutes and plug it into the time value. So here, I sub t is equal to 28 into the time value of the rule, and I get 15 times 28 plus 50, which gets me 470 liters. And then of course I can do the same thing with 52, and I get 830 liters. What this is saying in real life using the model is that at 28 minutes, the water tank will be filled up to 470 liters. For this one, at 52 minutes, the water tank will be filled up to 830 liters. And that's how we get the information that we want for the first scenario. For the second scenario, we're going to look at something a little bit more complex. In fact, the complexity of this one helps you with the PS&T because it's done in stages as well. If you look at your PS&T now, you'll be able to see it. But here, a water tank is initially empty, as in there's no water in it at the very beginning. A garden hose can fill the water tank 75 liters in the first 5 minutes. And then after that 5 minutes passed, the garden hose starts to lose pressure and can only fill 90 liters in the next 9 minutes. And hence, we need to determine a few things actually. We need to determine the rate in liters per minute that the hose is filling at in the first 5 minutes. So we just do the calculation 75 liters, of course, divided by 5 minutes, which gets us 15 liters per minute. Determine the rate in liters per minute that the hose is filling out after the first 5 minutes. You can see after 5 minutes, the garden hose loses pressure and can only fill 90 liters in the next 90 minutes. So 90 liters divided by 9 minutes gets us 10 liters per minute. So it's actually lost enough pressure to only like every minute it's actually losing it's actually not able to fill as 5 liters as much as you used to, so it's actually losing a bit of pressure there. We're also determining the capacity of the water inside the tank before the hose starts. It says that the water tank is initially empty, hence it's 0 liters, because empty means that there's nothing in there. But just as is careful here, we got to make sure that we also determine the capacity of the water inside the tank at 5 minutes, because exactly at 5 minutes is when the water loses pressure, and we need to know how much water has gone in there at that point in time. So in this case, we just take 15 liters and we times it by 5, and we know it's going to fill out 35 liters. Or ideally, I guess another way to sell it, it tells you that the garden hose can fill the water tank at 75 liters in the first 5 minutes. So it implies after 5 minutes, 75 liters has been filled. Okay, so no real calculation needed there. Now the table becomes more helpful as well because, well, we know that at 0 time that the initial capacity is 0 liters, and then we got 15 liters, and then plus another 15, and then plus another 15, and plus another 15. Of course, at the end we get to here, and this is where the water tank changes pressure. And so at this point in time, after 5 minutes, the water tank is no longer being filled at 15 liters per minute. It's being filled at 10 liters a minute. So what we need to do here is recognize that the next step is going to be 10 liters and the next step is going to be 10 liters. So this table helps you to see that before we had a table of values that would give us a straight line all the way up. Here we might have to have 2 individual lines, one representing the original rate of the hose and one after the rate of the hose is dropped. So we're going to write the rule in gradient intercept form for the first 5 minutes. This is the easy one because all we have to do is recognize that at the very beginning, this is 15 liters a minute plus nothing. This is plus 0 because it's initially empty. So I don't need to write plus 0 because plus 0 is redundant. It's a waste of time to write that. It's just C is equal to 15t, and 15 is the rate, so that becomes the gradient, and the y-intercept is 0, so there's nothing else written here because that's the initial capacity. Now, here's the important part as well. When you start writing your rules down, and the rules are now done in stages or legs, you got to make sure that you tell that this linear equation or model or rule only works when t is between 0 and 5. If it's above 5, of course we can't use this anymore because you would know that the water pressure dropped. So this only works for a specific set of values between 0 and 5 for t. Now, the next one is a little bit more difficult to gauge, and this is where you probably want to pause the video a little bit over time and really understand this. What about the 9-minute period, the period after the first period? Well, let's think about this. So this looks a little bit strange. I'll explain each step to you. It's 10 liters a minute, so the gradient is 10. That's still the same as before when we had 15. This is now 10. The y-intercept is also the same as before in the sense that at 5 minutes, 75 liters has been filled. So at this point in time, the y-intercept at that point in time is, I shouldn't say y-intercept, but we'll call it that for now, just because we sort of understand it. When time begins in the next period, it's at 75 liters. Now this is where it gets a little bit tricky. When t is between 5 to 14 minutes. So it's a 9-minute period. It starts at 5 minutes, as in after 5 minutes has passed, it's between 5 and all the way to 14 because 9 minutes. So it's 14, 5 minutes plus 9 minutes will get to 14 minutes. And we need to be aware that because time now starts at 5 minutes, remember 5 minutes has already passed, and this is technically now starting not at 0 anymore, it's starting at 5. We need to write here, instead of t, we've just replaced t altogether and now changed it to t minus 5 in brackets. This 5 value implies the beginning of when this new leg or new stage starts. So here time starts at 5 minutes, not 0, so it's t minus 5. And so when you put it in Desmos, here is what we need to do. You've got to be very careful. Here's the first rule. C is equal to, and I want you to just ignore the brackets and random stuff for now, but C is equal to 15t. That we already know about. But what we also need to be aware of is that we need to type this squiggly bracket in and to type in these values. These values are what we call the domain. So this is between the minimum value, so this is when time starts at 0 all the way to 5 minutes. So we're saying when t is between 0 and 5, we're going to use this rule. And then when we type in the next one, we go C is equal to this other rule that we got, which is when the second leg or the second stage of the water pressure, at that point in time between 5 minutes and 14 minutes, we're going to use this rule instead. So this allows us to construct a graph that has 2 lines connected together. And hopefully this graph makes sense. This graph is saying at between 0 and 5, it will go to 75 liters. And then you can see that the steepness of this line, or what we call the gradient of this line, but the steepness of this line is definitely more steep than the second line. And that makes sense because the more steep this line is, the higher the water pressure in this case. The more water is going into the tank per time. So here, this line shows us the 15 liters per minute, and then this line shows us the 10 liters per minute starting at that new point in time. In your PSMT, we have more than 2 stages, we have actually 3. And so you will probably have to have 3 different lines, and you will have to come up with these lines using the understanding that we've been doing through this water tank activity. So using this graph, still pretty straightforward. How much water is in the tank at 4 minutes? Very easy. We move to 4 minutes and go up and see that it's 60 liters. 6 minutes though, you can see it touches the blue line instead. And so if we go up to the blue line here, this goes to around, that looks like 85 liters. And so we tucked it in, fit 85 liters. So the graph still visually shows us how much water is in the tank at a specific amount of time, even with the second scenario. Once again, now with substituting values in, be careful here is that you need to choose the right rule for the right time. So if I want to know how much water is in the tank at 3 minutes, we're looking for the rule that makes the most sense. Do I put it in this rule when t is between 0 and 5, or do I put this in this rule when t is between 5 and 14? Of course, 3 minutes, 3 is obviously in between here, so I'm just going to plug it into this value right here. So substitute t is equal to 3 into 15t, and I get 45 liters. So at 3 minutes, 45 liters is being filled, whereas the other one at 12 minutes is not between 0 and 5. It's between 5 and 14. So I had to use the other rule, plug the 12 in to get my values and get 145 liters. So that's how you approach that task, is that you're able to come up with a linear rule for each leg or each stage, understand the time dynamics, so between a specific time to another specific time, and when you have 3 rules, you plug that into Desmos just like I showed you before, and you'll have 3 different lines combined together, and finally you can use that line or that graph and also or use the formulas to figure out how much distance has been traveled at a specific amount of time. So hopefully that helps. Remember, you can pause the video, stop it, and so that you can always check for it, think about it a little bit and then move the video on, and you can scroll wherever you want for that. If you have any questions, of course, your teacher is always happy to answer those questions for you. And if you have any questions for myself, then please just make sure you remember the specific part of the video that you're confused about and bring it to me, and then I can actually answer the question for you. So hopefully this helps. All the best. Keep working hard and you'll get it.